Hello, hello. Um, I'm Alan Szepieniec. I do. Okay. So I'm Alan Szepieniec. I do research for Nervos Foundation. I am a co-author on the marvelous family of Stark-friendly hash designs. And in this talk, I'll be talking about dark proofs, or rather, a set of techniques based on groups of unknown order. Please talk closer to the mic. All right. So this is joint work with Benedict Buns and Ben Fish. And in order to illustrate where this work is situated, one cannot do better than emulate the master, which in this case is Michal Ryabtsev, who plotted, using a Venn diagram, various popular zero-knowledge proof systems, and all of them either have succinct verification or trustless setup. There was this proposal back in the old days where you take a PCP and commit to it using a Merkle tree, and then open a couple of branches called CS proofs, and then at Crypto this year, a couple of individuals noticed that, hey, if you replace the Merkle tree by a vector commitment based on groups of unknown order, then you can actually get better performance. But the point is that the prover in these proofs is very, very inefficient. And that's why Stark is so extraordinary, because the prover is actually also efficient in addition to the verifier. And that's a property that dark proofs share with Starks. So obviously, if we have to compare dark and Stark, they both have succinct verification and trustless setups. Where they differ is in the underlying compilation mechanism to turn computation into a proof. Stark uses the stick protocol, or rather the stick is the information theoretical proof, whereas dark makes abstraction of whatever information theoretic compiler you use. In terms of the cryptographic primitive, Stark's uses hash functions, whereas Dark's uses groups of unknown order. And then what do we build from these cryptographic primitives? In the case of Stark, that's a Fried protocol or a deep Fried protocol. In the case of Dark, that's a polynomial commitment scheme. And the two are rather similar. Fried protocol is a commitment to a polynomial, which you then show has at most a certain degree, whereas a polynomial commitment scheme is a commitment to a polynomial, which you then evaluate in a particular point. So that's exactly it. It's a commitment scheme, so it has setup, which you don't have to trust. It's a commit to a polynomial, and then you open the commitment using secret information. But in addition to those three protocols, we require evaluation protocol, which you instantiate with the commitment, with a point in which you're going to evaluate z, and the value of the polynomial at that point, y, and you're going to prove that when you evaluate f at z, y is the result. We want the commitment scheme to be binding, same old property, but we want the evaluation protocol to be an argument of knowledge. All right? So diagrammatically, you can imagine the verifier selecting a point z at random, and then the prover has to respond by evaluating the polynomial at z and proving that this evaluation matches the commitment to that polynomial. And how do we build this? I'm actually going to present the protocol right now, but I'm going to make abstraction of the particular commitment scheme. I'm going to assume some homomorphic properties, and then later I will show you how to realize these homomorphic properties using groups of unknown order. So at the start we have the verifier, who possesses the full polynomial, and the prover possesses the full polynomial, the verifier only possesses the commitment to the polynomial, and both possess z and y. Z is the point in which the evaluation is queried, y is the value of the polynomial in z. And then what the prover is going to do is he's going to write out the polynomial in full, and then he's going to split it into the left part and the right part, such that the left part and the right part both have degree d over 2, or rather d plus 1 over 2 minus 1. You divide the number of coefficients by 2. And then the prover is going to evaluate the left part and the right part in Z, giving YL and YR, and is going to commit to both parts, sending both Ys and both commitments to the verifier. At this point, the verifier needs to check that when you append the right part to the left part, you still get the original polynomial, but he has to perform this check on the commitments. And this involves multiplying the commitment to the right polynomial by the right monomial of the degree d prime. This is an important feature that the commitment scheme has to provide. Supposing that that works, then the verifier can produce a random challenge alpha, and alpha is then used to compress the two halves of the polynomial. This way we get f prime, which has degree d over 2, which is just alpha times fl plus fx. And you have to do the same thing for the value of this polynomial, alpha times yl plus yr, and you also have to do the same thing for the commitments to both halves. So this is another property we need from the commitment scheme, that it has to allow linear operations. And then if you look closely at the top line, the blue text, and the bottom line, the green text, these are claims of the same form. Question? Sorry. Yes. So if you look at the top line and the bottom line, these are claims of the same form, except the polynomial involved has a much smaller degree. So we can recurse. And if you recurse often enough, then you end up with a polynomial of degree 0, which is just a constant, and you send the constant and check if it's correct. So what we want from the commitment scheme is it has to be able to commit to elements from an arbitrarily large set. Your polynomials have to be arbitrarily large, but your commitments still have to be, well, either constant size or logarithmic size. You have to be able to do linear relations. You have to be able to compute linear relations on commitments, and you also have to be able to compute monomial relations on commitments. So the question is, how do we do that? And the answer is we use groups of unknown order. We know 3 such groups. The first is the RSA group, in which you work with the integers and multiplication modulo an RSA prime, RSA modulus. And the only way to produce such a modulus is to sample the primes p and q and then multiply them. And that's why this group necessarily comes with a trusted setup, which is not really desirable. On the other hand, you can use the UFO group, which is also the integers modulo another integer n, but now this n was huge and sampled at random. So that allows you to set up without being trusted, but the problem is that these group elements are huge. And then the last option actually combines the best of both worlds. Here you have no trusted setup in class groups, and your elements are roughly the same size as elements in the RSA group. Unfortunately, none of these groups are post-quantum, so finding a post-quantum analog for these constructions is still an open problem. If you choose n to be a similar size as in the RSA group, then with high likelihood it will have small prime factors, which you can take out using the elliptic curve method. So you have to choose n in the UFO group, you have to choose n to be so large such that with overwhelming probability its factorization will contain primes that are large enough to make factorizing it as hard as in the RSA group. You can remove the small primes, but the small primes range from really small to almost infeasible. So I guess it's you have to decide where to cut off the process of removing the small primes. Another question. I was not aware of this work. Please give me a reference after the talk. All right. So we rely on two hardness assumptions. One is the age-old strong RSA assumption, and the other is the much newer adaptive root assumption. And despite the age gap, they are actually each other's perfect dual. So the strong RSA assumption asks to compute arbitrary root of a known group element, whereas the adaptive root problem asks to compute a given root of an arbitrary element. Both of these problems are falsifiable, which is either a good thing or a bad thing depending on whether depending on which camp you're in. So what can we use groups of unknown order for? That's where the acronym stands for. It's Diophantine arguments of knowledge. Diophantine has to do with, we're looking at polynomials defined over the integers. The coefficients are integers and the variables are integers. So for instance, Fermat's famous marginal note is a Diophantine equation. Bell's equation is Diophantine. Trigonometric identities, generally speaking, are not Diophantine because they involve transcendental or algebraic numbers. But if you really like trigonometric identities, there is a way to make them back into Diophantine equations. Arguments of knowledge refer to the fact that once you have such a polynomial, you can make the polynomial public and you can make part of the input public, and then you can prove knowledge of the remaining input. And Diophantine arguments of knowledge are really powerful, and I want to drive that message home with an example of a range proof. You know that in Monero and Zcash we have range proofs to prove that there's no inflation happening, and those are really complicated and they actually grow with the size of the range. And we don't need to have a proof that grows with the size of the range if we use Diophantine arguments of knowledge. So in our case, the prover holds a secret integer x, and the verifier only holds a commitment g to the x to this integer. And the prover wants to show that x lies in between L and U. So then he finds A, B, and C such that this equation holds. And it's not such a difficult equation. The sum of squares of A, B, and C has to equal 4 times U minus x times x minus L plus 1. So you can obviously see that the sum of squares has to be positive, which means that the left-hand side has to be positive, and it can only be positive if both factors are positive. So if this equation holds, then we know x lies in the range. And you may wonder, what's that 4 doing and what's the plus 1 doing? Well, those are artifacts of the algorithm that allows you to find A, B, and C such that this holds. So what the prover then does is he just sends commitments to A, B, and C to the verifier, and the verifier needs to apply some homomorphic operations in order to verify this equation in the exponent. And you might argue, yeah, well, how do you get those homomorphic operations if you don't have to send more messages? Well, sure, but you might have to send a few more messages, but they will still be constant size, irrespective of the size of your interval. This is something that we don't know how to do with any other cryptographic construct beyond groups of unknown order. So we have a powerful tool that works for integers, but what we really want is a tool that works for polynomials over prime fields. So the question is, how do we encode polynomials into integers? And the way we do this is you choose a large odd q, an integer, and you evaluate your polynomial in q. And that's the encoding. Because q is so much larger than p, this is a unique encoding. And even if you add two encodings over the integers, you get the encoding of the addition. So this is how linear properties hold. And even if q is large enough, you even get to multiply encodings of polynomials, and then you get an encoding of the product of polynomials. And you even get another interesting property, which is if you multiply an encoding by some power of q, well, that's the same as encoding a shifted version of the polynomial, or rather the polynomial multiplied by a monomial. Of course, the problem is q has to be large, but this is a problem we can solve, and I'll show you later on how. So getting back to this slide where I illustrated the properties that we need to have from the commitment scheme in order for the polynomial evaluation protocol to work. How are commitments defined? Well, that's just g to the power encoding of your polynomial. Linear relations are free because you can raise group elements to scalars, and you can multiply group elements, and that adds the respective exponents. Monomial relations, they are still tricky because the verifier has to verify that if you append fr to fl in the exponent, then you get fq, which he already has received in the previous round. But in order to append, he actually has to raise the commitment to the right-hand polynomial to a very large power of q, which is expensive. So what we're going to do instead is the prover sends both g to the right polynomial evaluated in q and the same value raised to the appropriate power. The verifier then checks this relation, and you might say, well, how does he check this relation? Because that's raising a group of unknown order to a very large power, and that's very expensive. Yes, it is expensive, but that's where we have Veselovsky's proof for. The verifier can outsource this expensive relation, expensive work, and in the end he only has to perform some small exponentiations. So this completes the polynomial commitment scheme. Then the next question is, what can we do with polynomial commitment schemes? And first of all, we have to place it in the proper context. So when you compile a snark or any zero-knowledge proof, you start with a computational claim, and you turn it into an algebraic representation using some arithmetization technique. And this arithmetic representation gets turned into an information theoretical proof, and then this information theoretical proof gets turned into a cryptographic proof using some kind of cryptographic assumption. So this illustrates clearly where dark arguments fit. They're an alternative to pairings and to Merkle trees at the bottom of the stack. But at the same time, it's worthwhile looking at what can we do in the middle of the stack with polynomial IOPs. So what can we do? Well, we certainly can use the same machinery that's used in Stark and just exchange the Fry protocol for our dark evaluation. And we can also achieve point IOPs, which is cool. And given these two things, we can get sonic, which is really nice. This allows us to get sonic without a trusted setup, which we call supersonic. And then there's, you know, the most powerful thing is the linear IOP, and we're not sure how to get that, but it would be cool because it actually captures a lot of existing SNARK protocols, or not even SNARK, but general purpose zero knowledge proofs protocols. But if you look closely, they can actually be captured as algebraic linear IOPs, which we can also do using multivariate polynomial commitments. So looking at this picture, we can do bullet proofs with logarithmic verifying time. We can do GGPR without trusted setup. So I think this picture illustrates better the dark web because we bring everything to the dark family. This is my last slide. I should mention that the paper is not yet online, but we are working very hard to get it online. So it will be on ePrint very soon, and possibly slightly sooner on my personal website, which is the line above there. Thank you.
So this commitment scheme, you can reduce it to actually finding the order of the group, or you need a different assumption?
Yeah, so these two assumptions, the strong RSA assumption and the adaptive root assumption, we build other assumptions out of them, and one of the assumptions that we build out of these is the order assumption. So if you can find an element with a known order, that breaks one of the intermediate assumptions, and it's trivial to reduce the security of the proof to it's trivial to reduce an attack on the interactive proof to finding an element of known order.
I see.
Hi, this was a great talk. How is the performance of operations on groups of unknown order compared to doing the usual modulo operations on RSA groups?
I don't have any experience in that respect. I would suspect it's similar because both use integer multiplication with integers of similar size.
Thanks.
Could you elaborate a bit on the exact groups of unknown order construction that you use, or at least suggest some references to read? Because well, it was defined like basically defined but not explained. Yes.
Yeah, class groups, there are a couple of references, but Johannes Buchmann is an author on all of them, so I would look up that name. He's popular, and sometimes he gets away with calling it imaginary quadratic cryptography, but it's really about class groups. And then, well, RSA, if you want to learn more about RSA, I'd open any standard cryptography textbook. And then the UFO group, that's a paper by Sander. I'm not sure where it was published, but it was published in 1999.
So Johannes Buchanan on the class groups?
No, Sander published on the UFO.
I mean, I was interested in the class groups.
Just the class groups. Yeah, I'd look up Johannes Buchmann, and then Chia has the interesting tutorial on how to use them. And there was another blog post by someone who's, yes, by Straka, very good blog post on how to use class groups in a cryptographic setting.
Thank you.
Okay. Okay. Let's take one last question and then move to the next speaker.
I just, because you were mentioning how you can instantiate all the different schemes based on the polynomial commitment construction, and I didn't see, and I can't imagine now how you would instantiate, I guess, like MPC in the head constructions, which maybe like now we'll hear from Kathleen, I guess. And also I was thinking more concretely about the GKR protocol, because it seems like the polynomial commitment is sort of like analogous in some way to this sum check protocol. So, I mean, do you have any kind of insight there? I didn't think too much about it right now, but.
Yeah, I would have to refer you to co-author Ben Fish on that particular question.
Okay, so let's spank. Let's not spank. Rather, we will thank the speaker.